In nuclear chemistry and nuclear physics, scalar or J-couplings, also called indirect dipole-dipole coupling, are mediated through chemical bonds connecting two spins. It is an indirect interaction between two nuclear spins which arises from hyperfine interactions between the nuclei and local electrons. J-coupling contains information about bond distance and angles. Most importantly, J-coupling provides information on the connectivity of molecules. In NMR spectroscopy, it is responsible for the appearance of many signals in the NMR spectra of fairly simple molecules. Vector model and manifestations for chemical structure assignments. The origin of J-coupling can be visualized by a vector model for a simple molecule such as hydrogen fluoride, HF. In HF, the two nuclei have spin 1/2. 4 states are possible, depending on the relative alignment of the H and F nuclear spins with the external magnetic field. The selection rules of NMR spectroscopy dictate that delta I equals 1, which means that a given photon in the radio frequency range can affect, flip, only one of the two nuclear spins. J-coupling provides 3 parameters: the multiplicity, the number of lines, the magnitude of the coupling, strong, medium, weak, and the sign of the coupling. Multiplicity. The multiplicity provides information on the number of centers coupled to the signal of interest and their nuclear spin. For simple systems, as in 1H1H coupling in NMR spectroscopy, the multiplicity reflects the number of adjacent, magnetically non-equivalent protons, nuclei with spins greater than 1/2, which are called quadrupolar, can give rise to greater splitting. Although in many cases coupling to quadrupolar nuclei is not observed, many elements consist of nuclei with nuclear spin and without. In these cases the observed spectrum is the sum of spectra for each isotopomer. One of the great conveniences of NMR spectroscopy for organic molecules is that the many lighter elements are nearly monoisotopic. 1H, 19F, and 31P each have spin 1/2. 12C and 16O have no nuclear spin. Magnitude of J-coupling. For 1H1H coupling, the magnitude of J provides information on the proximity of the coupling partners. Generally speaking, two-bond coupling, i.e., 1HC1H, is stronger than three-bond coupling, 1HCC1H. The magnitude of the coupling also provides information on the dihedral angles relating the coupling partners, as described by the K+ relationship. For heteronuclear coupling, the magnitude of J is related to the nuclear magnetic moments of the coupling partners. 19F, with a high nuclear magnetic moment, gives rise to large coupling to protons. 103RH, with a very small nuclear magnetic moment, gives only small couplings to 1H. To correct for the effect of the nuclear magnetic moment, or equivalently the gyromagnetic ratio gamma, the reduced coupling constant K is often discussed, where K equals 4π2J per hour gamma x gamma y. The value of J also has a sign, and couplings constants of comparable magnitude often have opposite signs. J-coupling Hamiltonian. The Hamiltonian of a molecular system may be taken as H equals D1 plus D2 plus D3. D1 equals electron orbital orbital, spin orbital, spin spin and electron spin external field interactions. D2 equals magnetic interactions between nuclear spin and electron spin. D3 equals direct interaction of nuclei with each other. 4 or singlet molecular state and frequent molecular collisions. D1 and D3 are almost zero. The full form of the J-coupling interaction between spins ij and ik on the same molecule is H equals 2 pi ijjjk ik, where jjk is the J-coupling tensor, a real 3 times 3 matrix. It depends on molecular orientation, but in an isotropic liquid it reduces to a number, the so-called scalar coupling, in 1D NMR. The scalar coupling leads to oscillations in the free induction decay as well as splittings of lines in the spectrum. Decoupling by selective radio frequency irradiation. NMR spectra can be fully or partially decoupled, eliminating or selectively reducing the coupling effect. Carbon-13 NMR spectra are often recorded with proton decoupling. History. In October 1951, E. L. Hahn and D. E. Maxwell reported a spin-echo experiment which indicates the existence of an interaction between two protons in dichloroacetaldehyde. In the echo experiment, two short and tense pulses of radio frequency magnetic field are applied to the spin ensemble at the nuclear resonance condition and are separated by a time interval of tau. The echo appears with a given amplitude at time 2 tau. For each setting of tau, the maximum value of the echo signal is measured and plotted as a function of tau. If the spin ensemble consists of a magnetic moment, a monotonic decay in the echo envelope is obtained. In the Hahn-Maxwell experiment, the decay was modulated by two frequencies. One frequency corresponded with the difference in chemical shift between the two non-equivalent spins, and a second frequency, J, that was smaller and independent of magnetic field strength, J, 2 pi equals 0.7 Hz. Such interaction came as a great surprise. The direct interaction between two magnetic dipoles depends on the relative position of two nuclei, in such a way that when averaged over all possible orientations of the molecule it equals to 0. In November 1951, N. F. Ramsey and E. M. Purcell proposed a mechanism that explained the observation and gave rise to an interaction of the form I1 I2. The mechanism is the magnetic interaction between each nucleus and the electron spin of its own atom, together with the exchange coupling of the electron spins with each other. In the 1990s, direct evidence was found for the presence of J-couplings between magnetically active nuclei on both sides of the hydrogen bond. Initially, it was surprising to observe such couplings across hydrogen bonds, since J-couplings are usually associated with the presence of purely covalent bonds. However, it is now well established that the H-bond J-couplings follow the same electron-mediated polarization mechanism as their covalent counterparts. The spin-spin coupling between non-bonded atoms in close proximity has sometimes been observed between fluorine, nitrogen, carbon, silicon and phosphorus atoms. See also Earth's field NMR, exclusive correlation spectroscopy, ECOSY, magnetic dipole-dipole interaction, dipolar coupling, nuclear magnetic resonance spectroscopy of carbohydrates, nuclear magnetic resonance spectroscopy of nucleic acids, nuclear magnetic resonance spectroscopy of proteins, proton NMR, relaxation NMR, residual dipolar coupling. Further reading: Gutowski, H. S. McCall, D. W. Slichter, C. P. 1951. Coupling among nuclear magnetic dipoles in molecules. Phys. Rev.